Okay, and I'll do a quick introduction for you. So today is our great pleasure to welcome Professor Shijing from the University of Washington to share her research and insights with us. And Shijing's group operates at the exciting intersection of material science, data science, and robotics, pioneering advancement in autonomous design for clean energy technologies. And in today's lecture, Shijing will discuss how the self-driving laboratories can augment and amplify human expertise, shaping the future of research through collaborative intelligence. And Shijing, we are truly excited to learn from your groundbreaking research. So please, the floor is yours.
Thank you. Thank you for the very nice introduction. And this is a great pleasure for me to be here and share some of the recent research in my lab. So to start with, I decided to have my lecture title as Building a Self-Driving Lab from Scratch. So from the title, you can see I'll be talking more about how AFO material science can be applied for experimental materials research. Let's kickstart. A little bit about myself, like you can see from my Zoom background as well as from my slides. And so I'm from University of Washington, and we are based in Seattle. And actually now it's the best season to come to visit Seattle if you have a spring break plan, because we have a lot of cherry blossom on the campus. But what I do as a professor, my lab mainly focus on how can we understand and foster collaborative intelligence. We want to amplify scientists' ability to apply artificial intelligence and robotics to accelerate our scientific discovery. So of course, just like everyone else in this room, we're interested in material science. Why we're interested in materials? Because fundamentally we know a new material have the potential to transform the world. One of the example is what I put currently on the slides. It's doped silicon, for example, for semiconductor industry, because we are able to manipulate the electronic states and also physical properties of materials like semiconductors, and that leads to the new industry of semiconductors, transistors, and a lot of the industrial advances came from it. Similarly, for electric vehicles, we probably have you probably have seen a lot of new electric vehicles in the past a few years, and fundamental technology enabled the wide spread adoption of electric vehicles come from batteries. And in particular, for example, lithium cobalt oxide is a layered structure, and a lot of the current battery technologies use lithium-ion batteries, and we use materials just like a lithium or cobalt oxide and its similar alternatives as cathode materials. So these are really great examples of how by working on new materials, it has a lot of potential for industrial applications, and that would impact our everyday life. But we have problems, right? As a material scientist, we want to try to design new materials. And the key challenge here is definitely there are infinite number of materials we can potentially design and try to synthesize. And one of the benchmark here I put is about a bit less than a year ago. We have a benchmark in the ICSD database. So ICSD database is the database that quite widely used in the community of material science that include a lot of the experimental records of the materials being synthesized in the lab. And you can see it's we hit 300,000 marks. So that's kind of a record of how many crystal structures we have that are synthesized by scientists and characterized by scientists. But on the other hand, I think a lot of you probably already learned from this course or just in the news. Outside the lab, in terms of computational material discovery, there are a lot of more materials out there, which are hypothetical materials, and scientists predict they're going to be really good for a range of different applications, but we haven't been able to synthesize them in the lab. So there's a widening gap in the way of how many new materials we can predict and simulate computationally, and how many materials we can actually synthesize in the lab. And the measure research is pretty much about like, okay, so what do we do about it? How do we really close the gap between like the theory and experiments, and how do we make our experimental work a bit faster? So it's kind of clear, right, to minimize this gap like between the number of materials we synthesize and the huge like design space and the number of materials we can potentially computationally predict, right? We need new ways to discover and optimize the materials. And translating that into a laboratory space, we want to find new ways to synthesize and characterize materials in the lab. This is faster than the traditional bench chemistry. So here comes like the idea of self-driving lab, the emerging like autonomous labs, often like involved in like pretty much like those three things like we are upgrading like in terms of our experimental procedure. So instead of bench chemistry, now we have robotics in the lab. I will perform automated synthesis. Instead of single sample studies, we try to have like automated characterization, which allow us to screen a large number of materials and give us feedback about what they are, like how they work, and helping us to understand them. And of course, like instead of purely relying on domain expertise analysis, a lot of times machine learning has been like incorporated in the data analysis process, and this allows us to process a vast amount of data in like a batch fashion, and that really speed up like the data analysis process. So if you think about like the three things is like on the right side of this slides, and that means like we are now really like studying like the interactions and also about like the collaboration modes between like the high throughput synthesis, characterization, and machine learning. And a lot of its design of self-driving is really about like, how do we like place the automation and the artificial intelligence with the idea that this framework can help us catalyze materials discovery. So if a scientist have a greater idea, and very quickly through this self-driving lab framework, we have the old technology get updated to new technology. All right, so that's kind of like my quick intro about like the frameworks we are trying to build with our like autonomous lab or self-driving lab. I use those two terms kind of interchangeably, like about like how we update like the idea of the lab of future. So like now if we think about like we know what we want to do, right? And then the question is how we do it. So like if we think about the lab of future, we want it to be faster than what we have currently. And we want it to be more accessible. So in the ways like a lot of people like can access to self-driving labs instead of just like a one person, like, get host to many robots. So we want everybody to have their own robots. And of course, like we don't want to just have the robots, we want to have the artificial intelligence, so like embodied in our robots. So like we can have the AI scientist, like in the form of like performing robotic work in a more collaborative fashion. So in the next like half an hour or so, like what I'm going to do is I'm going to explain like 3 steps for us to like develop a self-driving lab from scratch. I'm going to talk about like how we design a brain for our like robotic systems, how we use some of the techniques such as the computer vision to like figure out how we examine materials like in self-driving labs. And then I'm going to talk about building the body of a self-driving lab is actually to like start like putting together like the robotic hardwares like we are interested in using. Okay, so first topic, having a brain for our robots. What does it mean? Well, I mean, if you want to have like a design of a brain of a robot, the easiest like to start with, imagine if you already have an automated lab. So here is like a short video, and this is actually taken from my collaborator in like PNL, so Pacific Northwest National Laboratory. And the idea of this automated lab to start with is that we have multiple robots, including the robots that we use to transfer samples between different stations. and they kind of work together for us to like perform a thin characterization as well as kind of like later on lead to like analysis in one go. So what you have just seen is like a example experiment, which is to make a redox flow battery materials using this automated lab. And as I said, this video is from our collaborator at the Automated Robotics for Energy Storage lab in PNL. So you can see it's like if you already have like a number of hardwares to work together, that means you're able to already have like an automated workflow, right? Like for the experiment that you have in mind. So in this case, specifically, as a case study, we want to improve the aqueous solubility for fluorine-based annulate for higher energy density for our flow batteries. And the challenge we're tackling is like we always have a low yield at a mild synthesis condition. So the design of this experiment is that we want to find the optimal conditions allow us to have a high yield of the sonification reaction here, like shown like on the left side of the slide. Of course, this is kind of a collaboration between UW, where I'm from, and the PNL with my colleagues and collaborators on the slides shown there. Okay, so let's think about like how do we design like the experiment? Now we already have the robots. So a simple like design space would be, okay, let's change the temperature, change the precursors, change the concentrations, change the reaction times. So that's kind of like a 4-dimensional space, and we're very fun with like the boundaries of what like the scientists believe, like we're able to find like a better condition within this boundary. So quick back of envelope calculation, we found out, well, actually, if you want to fully explore this design space of 4-dimensional design space, we need more than 150 million runs of the experiments. That means the video everyone just saw, we need to run them over 150 million times. Well, this is not practical because if you really think about it, it transfers into like more than 10 years. So this becomes clear. Even if you already have a robotic laboratory, the goal is not to just to screen everything. So the key point here, we want to design the brain of our self-driven lab in the way that we are moving from purely high throughput screening to minimal experiments needed. And that really comes from like the idea of like the algorithm design. How do we coordinate and plan experiment in a way you only need to do a minimal amount of experiments? So over the past year, one of the projects our lab have been doing is really to think about like well, we design like a optimization framework, like so in the way we every time we receive the characterization results from a self-driving lab, and we build a surrogate model. And based on the surrogate model, we have a decision-making policy. And then the decision-making policy would lead to a suggested next round of experiment to do, and we pass that to the robotic synthesis module. Okay, that sounds like it makes sense. And in particular, in terms of the algorithm you can use, I think quite a lot of you have probably heard of Bayesian optimization by this point. Maybe like you have also heard about Bayesian optimization is part of the active learning like methods, which can be like used for us to guide experimental design. So in this case, like a study, MATLAB used batch Bayesian optimization. That means like we start from like the design experiment. Often you can start with sampling randomly, or you can sample sample the design space with a grid search. So you get some initial idea of like what is your like design space like. So in this specific case, we have a 4-dimensional space, and like round one, like we have a batch of like an experiment, and that leads to like the like initial idea of what is the like optimal regions, and what are some like the less desired regions. And in this case, like we can start to build a surrogate model, and we use the Gaussian process regression, like regression model in this case give us like both like the predicted posterior mean as well as the uncertainty of the prediction. So in this case, we are able to map like a 4-dimensional space. And you see, I show 3 cubes here because our eyes are very good at seeing like 3 dimensions, and the 3 cubes kind of give the idea of the 4th dimension, in this case, temperature. But then we obviously feed the information back to our Bayesian optimization framework, and we can have a balance of exploitation, and our Bayesian optimization framework keeps suggesting where you should sample next. And we did 3 rounds of iterative sampling, and then after those 3 rounds, we realized, oh, it's actually very powerful, because in this case, totally each round we sampled 15 of conditions, and then 3 rounds, that means like we have 45 samples. Even with those 45 samples, which is actually not a big number comparing with how many the total number of experiments we could potentially do, but we can already see on the right side of the slides, we have some very bright yellow regions. In this case, you can see the optimal regions where the highest yield was kind of obtained, was already very visible, even with these 45 samples. And the trick here is actually you learn each round, and so that means there's a kind of active learning process instead of just sampling a lot of the data and then learn from everything in one go. But there's a little bit of additional details here, because in the design of our Bayesian optimization framework, we quickly realized the 4 dimensions we've been sampling from are not just a unconstrained a free sampling process, because in our synthesis step, we actually had 2 steps within it. We can mix all the precursors and we need to heat them. And the heater is actually our rate limiting step. We have 3 heaters, and that means all these 15 different samples or different precursors, they have to be somehow allocated onto those 3 heaters. So that leads to kind of a discussion about how do we sample in a constrained 4-dimensional space. In this specific project, we had 3 different models. We test about we sample in 4-dimensional space, and then we cluster the one of the dimensions into the 3 temperature we have, which are on 3 different heaters. We also tested temperature redistribution as well as temperature pre-selections. But what all does this mean is you can start to have different ways you can constrain the design space you have, and you can build that in your Bayesian optimization framework that allows you to be more flexible in terms of how you sample from a large space. And in this specific case, you see the 3 models I just showed, which represent the 3 sampling strategies. We found out actually model A was the best, and model C was actually kind of comparable to just with random sampling, so it's not very effective. And the idea here is we realized the more flexible sampling strategy was the best in terms of it gets the more conditions give us the high yield very quickly. So the lessons learned from this case study is that if we just start to use active learning, in this case machine learning models, to help us to sample a large space, we want to have the minimum number of experiments to do, it's not hard to have an okay model, and you'll be fine. You feel, oh, I start to learn something about my space. But if you really pay attention to how you design your Bayesian optimization with different sampling strategies, you can have a good model. And if you compare different ones, if you look at the really smart models, you actually need to consider how the Bayesian optimization you're designing kind of correlate with the hardware limitation you have. And in this case, we deliberately make it more flexible because we have a constraint of the 3 heaters versus the 15 different precursors we can select in one batch. So with this methods, what we actually learn in terms of the material science is that we presented using this active learning methods, we can quickly determine what are the list of conditions give us the high yield in terms of our active materials we want to make for our flow batteries. And like what we want to do here is we are able to find a range of good conditions, give us high yield, but they also have like a lower synthesis temperature needed and a lower sulfonating agent needed. So our recipe, after optimized using our active learning methods, becomes more energy efficient. So that's kind of a case study to share a little bit of like how do we design a brain for our robotic setup. Let's move to the next point, eyes. How do we change what our robot is seeing in an experiment, and how does that relate to our design of the experiment? So the case study here, I want to show is about a microstructure design. So which is typically is like a challenge we see a lot in material science and often that relate to the characterization. So on the left side of my slides, I put a scanning electron microscopy image. And the first question is like for domain experts, which is us in this lecture. Do you think it's a good film or a bad film, which actually this is the sample way imaged? You may already have some thoughts in your mind if it's good or it's bad. Well, if we give a bit more information, so this image is actually a thin film semiconductor with the material of silver bismuth iodide. And silver bismuth iodide is a wide bandgap semiconductor within the family of like a range of silver-rich and bismuth-rich compounds. And if you ask the same question to my collaborator from University of Oxford, in this case, it's Professor Robert Hoy. If we interview him, he'll tell you, well, this material is a pretty good semiconductor for indoor photovoltaics. But at the moment, our current reported solar to electricity efficiency is much lower than its theoretical maximum. And one of the reasons it's hard to make a really high efficient solar cells is that you may see those pinholes in your semiconductor films, as we see from this scanning electron microscopy image. So there are features in this image we don't want in our solar cells. So that's kind of leads to we need to optimize the way we make a thin film semiconductor. So before I introduce a lot of the machine learning, the one quick thing we can do is if we step back, how do we learn from images, right? That's kind of the fundamental question. If we start with a raw image, and if we really want to do a proper image analysis, we probably will end up using some sort of software and give us a digitalized version of the defects we see in the raw image. So in this case, it turns out to be 16% of the image actually contains those defects in the form of pinholes. Well, that's fun. Now we have a defined problem, which we can just teach a machine learning model to do the same thing. So in this case, in my lab, we developed a computer vision framework called DAISY. So it's DAISY image interpreter. And we can automatically extract information from these microscopy images. So the actual model being used here is one of the neural networks models, so deep learning. We use deep learning. And the idea here is we classify whether an image is defective or not. So it has a pretty high accuracy. The accuracy is over 95%. In this case, it's 97%. And of course, there are some additional techniques used here, such as data augmentation. So we want to increase the number of training data through dividing the existing microscopy images into patches. But at this stage, we can define defective images. But a challenge arises. The information we get does not really equal to the insights we get. As a material scientist, we want to have the insights from an image beyond the statistics we extracted. So in this specific case, it means we want to distinguish what are the pinholes and what are the grains. So far, our model only know if it's defective or not defective, but it doesn't really recognize the grains. So how do we teach our model like there are grins and pinholes both in the image, and we want the statistics from both. So what we end up doing is like we use actually not one machine learning model, but a compound machine learning model kind of like work together to achieve this goal. So in addition to what I just showed in the previous slides, which is the classification, which allows us to tell if it's defective or non-defective, we combine it with an open source model developed by Meta called segment everything. So we also segment the image, which gives us like different features are all picked up by the segmentation model. Of course, we have to fine tune the segment everything model. We can't just directly use them because typically, like in open source, like image segmentation, like software or framework, they didn't train their like original model using microscopy data, right? For other material scientists, we need to make sure it's like the features being segmented are relevant to our problem. So we fine tune the segmentation model, and we combine that with our classification model. And then we have a third model, which is called a clustering model. So here we use the k-means clustering, which allows us to separate the grins and pinholes. So you see, with the three models combined, now, if you give our DAISY framework SEM image, it will tell you the defects as well as the grin characteristics. And the model now knows what a grin is a grin, a pinhole is a pinhole. So like so that's kind of like we are giving our models the materials relevant context by having multiple machine learning models working together. Okay, so then come to the next question. Well, so okay, so our models, we have the eyes in the ways like they see the images, they can directly like analyze them. The next question is like, how do we feed this information back to the synthesis? So what I just showed like in my previous slides, how these like images like were measured. They are based on like the spin coated thin films, and in fact, those those like spin coated thin films were made by those 4 steps: preheating, spin coating, anti-solvent addition, and annealing. In fact, the database we have were 27 combinations of these like 4 steps out of a total possible combinations of over 1,000. So in fact, it's over 1,700. And of course, we already have the eyes in our system. Our computer vision model can quickly extract information from like the microscopy images. The question is like, how do we feed this information back to the synthesis space, allow us to make the next films with fewer defects and larger grins? So let's take a step back. It's not an easy task because our historical data are biased. If we think about like our like data set we currently have, like our scientists, we decided the conditions we want to like play around with, and typically that's not like evenly distributed across the full parameter space. So what we end up doing is actually we end up designing like a reinforcement learning agent. So like, in this case, we use the Q-learning as like our model-free reinforcement learning. And then we have the agent to learn from the historical data set, figuring out what is the best set of conditions lead to large grins, lead to fewest defects, and then it starts to suggest like new conditions outside the combinations currently tried. So in the end, this like synthesis planner end up to be a one-shot learning. So we trained based on historical data, we suggest a new suggestion. And what's the advantage of using AI agent instead of say like using like just say we are ourselves human designing these systems? There are many advantages in terms of speed, but the most interesting like takeaway from this study for me and for my group is that we realized like the historical data set and also like when the agent was learning, it tends to like suggest or tends to identify in the synthesis space like anti-solvent assistant conditions, and we say that would be the best. by using an AI agent, it allows us to like quickly jump out from like the design space like we are familiar with. We should like based on prior information and our previous like understanding, that would be the best condition. So it actually allows us to like think a bit outside the box and suggested the conditions for us to try, which is it turns out to be equally good without the solvent, but in a synthesis space that is a bit further away from what we've been like trying in the past. So this is very interesting, right? Because combining like the automated image analysis and the agent trying to design experiment, it allows us to explore like a different region in terms of synthesis space very quickly. So we are able to go beyond our own knowledge and potentially bias we have in the past. Okay, last topic, bodybuilder. Okay, so like from this kind of like introducing the algorithm into our design of experiment and design of new materials, we quickly realize, well, maybe we can condense everything on a benchtop. So like the idea here, this is kind of an example of an open trunk liquid handling robot we have in our lab. And more specifically, what we do is we have a Python like an API controlling this liquid handling robot, and we programmed it, and we use that to make microorganic frameworks. So microorganic frameworks, in this case, we made like a cobalt-based MSE403 is a nanoporous material for hydrogen storage and CO2 capture. So it definitely have like a potential environmental applications. That's why we are interested in them. So like it didn't take us long to realize like the robot can make the materials like as the ones we want, as good as the procedures a human take. So we verify the robot can make these meta-organic frameworks. But the challenge really comes from like how do we design the characterization feedback? Well, typically we would use X-ray diffraction method, but like not surprisingly, I didn't have, or I still don't have an X-ray machine on the benchtop. So what we end up doing is like we figure out, okay, maybe using microscopy is also like a way for us to distinguish what is the desirable meta-organic framework we want to make and some of the common set product. So in this case, we realize like optically they are different. So this allows us to use a high throughput optical microscopy as alternative to our X-ray based structural characterization. So we start to build a proxy like in terms of our characterization. And this allows us to accelerate the characterization by, again, bringing computer vision. So that's kind of the eye designing part. And we can quickly go through like the products of a synthesis of the experiments. And as a result, if you show our computer vision model with like a raw image, have some crystals, we can quickly distinguish where are the crystals, how many of them would have been made. That's very like handy. And this leads to like, the creation of a database we made, like based on like the synthesis of meta-organic frameworks, as well as like the microscopic images collected and the computer vision algorithms, which extract the information automatically from these images for us to get the next synthesis loop. So if you think about it, if we compare the computer vision-based image analysis coupled with our robotic system, well, we are like currently in the regime of around like 40 times acceleration compared to our like manual analysis. So and this is kind of like the state of art for like a number of self-driving labs in the world, or where we are probably like in the region of like achieving more than 10 times acceleration, like as our kind of like a routine like design of different automation like pipelines. But at this point, that means we can actually start to design hardware. We can bring in more inline characterizations onto our robotic system. And this is kind of an example of some of our like hardware designs and 3D print them, put them more as a part of our like a modular robotic system. And what you end up to see here is kind of like a bit more like a fulfilled like open trunk like a robot. In this case, you see we have multiple like modular systems, like each of them become this own station, and we can start to bring in additional characterizations like for different projects in this way. So what you can see now is like we are kind of starting to burn everything on the benchtop, but in a modular fashion, and allow us to have this autonomous loop of design experiment. So if I want to go one step further about self-driving lab on a benchtop, we can actually build everything from scratch. Well, this is what I said in my title at the beginning of the lecture. So here at the University of Washington, like we have a number of projects are based on Science Jubilee. And Science Jubilee is a project like about like a really designing multi-tool fabrication, and started by my colleagues here, Professor Nadia Pig, as well as Professor Lilo Pozzo. They've been working on some of the open source lab automation like hardwares. We adapted it, which means we ordered some frames, and then we have a series of like components. And this is the last summer, and our students start to follow the open source like hardware system and start to build a robotic system. And now if you see what we've been doing in our lab is to really build like our own like a scientific robot. And you see on the right side, this liquid handling robot like built from scratch, like following like our open source hardware system. It works pretty well. Like this is the kind of a demonstration where like the color mixing can be like achieved using like our like robotic system built in-house. So you can see that now like we can start to summarize different theme of self-driving lab concepts. Like here, like we are borrowing like the framework like of self-driving cars. So from a level 0 to level 5, we can formalize by saying we can have a higher autonomy as like we design the different types of self-driving approaches. Like we can have like more and more tasks being automated. At the same time, we can also increase our task complexity in the ways like more and more communication, decision making are done by AI without a human in the loop. So for everyone, if you are interested in AI for science, self-driving lab projects, you don't always have to go for the full automation. Like you can find like what you need and then find yourself like in one specific spot like within this framework of the level of autonomy and the level of task complexity. With that, I'm going to summarize like what I've been talking today. So I mainly talked about like some of the case studies, like how like we can have like self-driving labs to achieve 10 to 100 times acceleration in terms of our typical experimental workflows. And really the trick here is that we need to design the brains by working into like the smart algorithms to control our robots. We do often need like think about like what information we extract from like the laboratory environment. That's kind of the eyes. Often we use computer vision to help. And of course, like we can also extend the self-driving lab idea. Instead of purchasing commercial valuable solutions, we can start to build like different hardware that is customized for the specific material science problems you are interested in. With that, I want to thank everyone in my group. So everything I presented today is kind of would not be possible without the collaborators as well as the students and the researchers in my group. So with that, I think we have probably 2 minutes to answer some questions. I would love to like answer any question you have.
Great, thank you so much, Shijing. It's a really amazing talk. And it's spot on because actually as the students from this course have been exploring the active learning in their assignments during the recent weeks. So I think you really show them how the cutting edge science, how the active learning can be utilized in the cutting edge science. So speaking of that, I'm not gonna use my privilege. So I'll leave the time for others' questions. And if you have any, just feel free to unmute yourself.
Yeah, I see in the chat you mentioned like for pattern recognition, you're also working on computer-based vision-based pattern recognition, I guess.
No, yeah, because like from your talk, you mentioned like how does human eyes process
Yeah.
images, and how do we identify whether there's a defect or this location existing. And I think, yeah, that computer vision stuff. Yeah, and
Got it.
actually, yeah, if others don't have question, I have a few. Um, so actually, I'll start with like a high level question, like because we always keep talking about like human in the loop, but it's still not quite clear to me how can we mitigate the influence of human bias, like subjectivity we incorporated in that loop, and also how can we like instead of just having an expert sitting there labeling the data or chatting with AI agent to decide which should be the next step, how can we effectively accelerate the throughput of this human part? So because I feel that's a bottleneck that limits the whole speech, right? So do you have any like suggestion, insight on this?
Yeah, that's a very good question. Personally, I'm not like a fan of having human labeled data, especially like if we have a lot of data to like label. But the challenge is like in our material science, there are not that many well labeled data because the label comes from domain
Yeah.
expertise, which comes from like years of training. So like currently, looks like what we've been like kind of like moving more into is that so instead of having the human and the, like the AI or like the robot trying to perform like the similar task, we try to design like our like experimental flow in the way they perform complementary tasks. So what do I mean is like if we want to have like the human kind of like performing the similar tasks, for example, like predicting like the properties or even just extracting information from image or label them, like human would be slower than like the algorithm. Just like how we make like samples, human would be slower than the robots. So like in terms of throughput. So I would just like train once and then have the like automated system to perform those tasks. But the human does bring a lot of the complementary like kind of like a skills. And for the moment, it's like just like what you mentioned, the communication, for example, is deciding what is important to study. So these kind of like tasks are more like very domain specific and very, very human involved. But the high level philosophy is like to have a human and the automated system perform complementary, but not the same tasks where the human would pretty much like feeling is like they are going to be slower than like the automated systems.
I see. This is really amazing, a very interesting idea. And I see, like from your computer vision work, you are using like clustering to identify these different classes of the patterns instead of labeling all like to use a human to do the label. So my follow-up
Yeah.
question on that is, do you think if like how can we be informed if there's any like mislabeling happens if we just let the machine to automatically perform all the analysis? And if there's any, do you think that like considering the portion of this mislabeling, would it actually bring any effect on the performance or the accuracy of the results?
Yeah, that's a very good question. So firstly, it's like definitely we use like unsupervised learning more and more nowadays for the tasks we can design to be a super unsupervised learning challenge, so human doesn't have to label it. But you're right in the ways like it does come with the potential of having like it's called machine bias, let's say, like also have like the mislabeling. So it's like so there are two things we typically do. One is like with with a reduced number of tasks the human have to go through, but we still need to have a human serving as a kind of supervisor role. This is kind of like a level 4 autonomous like a lab. It's kind of like a human is still part of the system, but it's more at a supervising capacity. So this allows
I
you to do a
see.
little bit more quality control. And then the second point relating to that is that like so often it's like it's hard to know what is ground truth. So it's like
Yeah.
even among different human experts, like there may be different like opinions or different like ways we analyze the same image or the same data. So so then it comes to like the question about like having more diverse data set, having like a more like a robust system in terms of using statistics to come over a lot of the potential outlying conclusions. So that's kind of like one thing advantage of using AI or using statistical method is like the statistical method allows you to learn from the data.
I see. Thank you so much. And actually, because we are 5 minutes out, I wonder if you are still okay with more questions, or we can just call it a day.
I think we have one more question. I see in the chat.
Oh, yeah, great.
The question is that is the mirror system coupled with spectroscopy and high quality camera? So the answer is yes. We do have like a spectroscopy coupled with mirror now, and the high quality camera. We do have a camera, so I guess that's kind of a question of like what does it mean? How high quality we want. But in short, to answer your question, yes, mirror system comes with a spectroscopy. It doesn't have to be spectroscopy. It can be other characterization tools. But the idea is like it's modular. You can bring different characterization unit to it. So we have both like camera and like a spectroscopy on it at the moment.
I see. Hi, Shijing. So I asked the question about this spectroscopy thing, because I noticed that in your slides, I think one of the slides shows that like you have a spectroscopy probe in the mirror system. Yeah, so I'm asking a question because I'm curious about this. Is it just like for a probe from a spectroscopy, or you actually have a spectroscopy next to the system? Like it. Did you get the question?
So just to make sure I understand, you asked if I have a probe or if I have a the probe is connected to a spectrometer.
Okay, I see.
Yeah, we can also like discuss more offline in terms of which vendor and so on.
Yeah, sure.
Yeah. So yeah, so in short, the probe is connected to a spectrometer.
Okay.
Yeah, thank you, Shijing. And if you are good with time, actually I have one more question.
Sure.
Okay, so actually it's a little bit basic question. Speaking of active learning, but I'm pretty sure like all the students may enter the same question with me. It's like how can we because like when designing our active learning framework, there could be lots of like hyperparameters. For example, like which kernels should we use to capture like the signals. Also, like how can we evaluate which acquisition policy or which kernel set would be optimal for the given task. So do you have any idea, like suggestions, how can we proceed with that?
Yeah, that's a very good question because a limitation of the active learning technique directly applied to experimental research is that we don't really know the ground truth when we start.
Yeah.
And we're actually not sure like we have the ground truth in terms of we learned everything about the system when we finish. So that's kind of like a limitation. So now like we definitely see like kernels affect the sampling, and we definitely see like the as I showed in my slides, like how your sample affects the learning rates, and that's we kind of see that like the effect very clearly. So more and more what we've been moving towards is like we try to increase the amount of virtual understanding before we actually conduct the experiment. So we try to have maybe physics informed or have some sort of modeling to help us understand the landscape a bit better before we just go with pure statistical methods. And the secondly is like I think there's a lot of value of having a toy like trials before launching like a large experimental campaign of active learning. So it's like so if we start to know the system a little bit, and you can set it as a prior, as a constraint in different ways, and that would help you like to get to like the like scientific outcomes quicker or like more confidently. So I would say it's like would try to do more virtual work to start with, and try to start with a toy problem to understand the manifold a bit better before like the large scale experimental sampling would help.
I see. Thank you so much. I believe that will be valuable to the students.
I have a follow-up question to that actually. Is there any reason why we cannot use active learning to optimize which kernel to use and which acquisition policy to use? Like, is there any reason why we cannot use active learning to design active learning, which then do the experiment?
There's like a like, I mean, nothing wrong. It's like actually it's very much like encouraged. Like you can definitely like try to like optimize your kernel and using active learning to optimize parameters, hyperparameters like of the Socrates model or like of the like actual sampling policy. There are like a kind of a, I would say like quite a few studies on like how do we like have flexible sampling strategies, and maybe each round you also learn something and you optimize from there. It's actually very much like encouraged. I don't think like there's nothing. I don't think there's anything stopping us doing that. I guess my previous comment was more on like the fact is like we don't know what we don't know. So in a ways like we can use active learning to optimize the kernel, to optimize like the parameters of our Socrates model, but they are going to be as good as the samples we currently have. So it's like we don't know what we don't know in a way for the design space, the area we never sampled. So sometimes we need to make some educated guess.
Yes.
And I think, sorry, you go first.
Yeah, it's like if we just keep optimizing, eventually the system can just optimize itself and we don't have to do anything anymore, right?
For
the system, yeah. Like the system will just go optimizing in higher and higher level. Eventually, we don't really have to do anything. That's what I'm guessing.
I think you're right in the ways like if we keep optimizing the model and the system, it will become more intelligent, it will become better. So I think like the idea is like depending on the goal of your like study. If your goal is to get a better model, better system, in terms of better intelligence, then definitely we try everything we can to feed more information to the system, and ideally like this can be automated, right? So it's like a self-learning. And like I guess the other question is if your goal is to find a new material, and like it's not always the case that most intelligent optimized model would be the one that find that material. So it's a little bit more complicated in terms of like what's the approach. So then it comes to the other questions like how do you balance the physical information, like the first principle, like knowledge you have, and then the intelligent system which like you designed it to learn and optimize over time.
Okay, thank you.
Yeah. So Phil, I think back to your original question, actually to me it's like a different way to do with the QBC method, query by committee, where you can design an ensemble of the models, and as you keep collecting the data and measuring the disagreement between the models, you are making these models or making your whole model more informative. And to your second question, so actually like what Benji shared with us last week, the next step for the whole domain, for the whole area, is to answer the question, how can we develop like an AI agent that can win the Nobel Prize? How can we train an AI that can self-learn and then just beat like other scientists? That would be the alternate or like the current goal for the domain. Yeah.
It's like if AI can win a Nobel Prize, why do human researchers still need to exist?
We need to build that AI, right? And also like that's still a very long way to achieve that goal, right? Yeah, that's the ultimate goal in the domain, I would say, but may require years, like decades.
I mean, I would say AI already won the Nobel Prize. No, it's just like we wanted to win the materials, like in the materials like domains.
Yeah, like let AI to be the person to win the Nobel Prize and get that award. Yeah.
I see.
Yeah. And I think that's it. And thank you so much, Shijing, for sharing your insightful and groundbreaking research with us. And we truly appreciate your great talk.
Thank you. Thank you all.
Yeah.
Have a nice
Thank
day.
you. And
thank
have
you
a great
for having
day.
me today.
Yeah, our pleasure.